In this chapter, we're going to be introducing antidifferentiation and integration. In this lesson, we're going to look at solving differential equations by separation of variables.
Okay, hi everybody. So in this lesson here, we're going to take a look at the method of separation of variables. This is about solving, very, very simple, what we call differential equations, okay? And what we mean by that is these are going to be equations that have a derivative in them. Now there's a lot of vocabulary associated with that. I'm not going to get into that right now. What we're looking at here essentially is we're going to look at a situation where we've got the derivative, and the derivative is going to equal some function of x and y. Okay? Now, when it's written like this, that doesn't really help us out that much. So we're going to change the notation just a little bit here. What we're going to do here is instead of writing y prime, which is what we've been doing this whole course, we're going to go back to this notation right here, dy by dx. Okay, so the ratio of differentials here. Now, where separation of variables is really useful and easy for us to work with here is when we've got, like let's say a ratio of expressions here. Let's say this is g of x over h of y. It doesn't necessarily have to be an irrational. It can be different than that. But what we mean by this is what I can do here is I can, in essence, cross multiply and make this h of y dy equals g of x dx. In other words, what I can do is I can get the parts of the expression that are functions of y and combine that with the differential of y, just like I can take the part of the expression that's a function of x and combine it with the differential of x. Now, if you look at that notation, okay, this is almost at an integral here, and so now what I can do here is I can integrate both sides of the equation. And what I'll get here is h of y plus some arbitrary constant is going to equal g of x plus another arbitrary constant. And then from here, what we end up doing as much as we can, solving for y, combining the arbitrary constants or any kind of constant values that popped up here, to get the final result here, the final equation here. Now, that's not always easy to do. Sometimes we just have to leave it as a function of both x and y. But that is kind of the goal here, to then at this point take it down, and if you can, y equals something. Anyway, it probably makes more sense to take a look at some examples. Okay, so here's an example. So dy by dx, or the derivative, is equal to 2x over y. Now I want to solve for y as a function of x, if I can. Okay, or at least have some sort of relationship between y and x, not including the derivative here. Well, but this is separable because I can multiply through by y and I can multiply through by dx to get this expression right here, this equation right here. Then what I can do is integrate on both sides. And I mean, I don't have any intervals of integration, so this is just going to be an antiderivative. And the antiderivative of y will be y squared over 2 plus some sort of constant here. And this is going to be 2x will be 2x squared over 2, and the 2's will cancel, so x squared plus another arbitrary constant. Now, if I can, I'd like to get the y by itself, so I'm going to multiply, this is a second arbitrary constant. I'm going to bring the c1 by c2 over. And so arbitrary constant minus an arbitrary constant is just another arbitrary constant, and I'm going to leave it like that. I'm going to multiply everything through by 2, so y squared will be equal to 2x squared plus, well, 2 times an arbitrary constant is just an arbitrary constant, so I'm just going to leave it at c. Now, at this point here, I could leave it like that if I wanted to, or I could say that, y is equal to the positive or negative square root of 2x squared plus c. And that would be fine. Probably just as good to leave it at this step right here, though. But that's what we mean by separation of variables and then finding the antiderivative. Okay, here's another one. So I've got a y prime there, so what I want to do to make my life easier is I'm going to rewrite that using this notation. So 6x squared over 2y plus the cosine of y is going to equal dy over dx. And now, again, I'm looking at this, I can separate those. Make that 2y plus the cosine of y dy is equal to 6x squared dx. And then I can integrate both sides. And the integral of 2y, well, I'll raise the y to 2, divide by 2, so it's going to be y squared plus, and the antiderivative of cosine of y will be the sine of y plus an arbitrary constant, and I know I'm going to get one on both sides here. Here, the antiderivative of 6x squared will be 6x cubed over 3, so that'll be 2x cubed plus another arbitrary constant. Now, I'm going to bring those two arbitrary constants together here, but this is an example of a situation here where, you know what, and remember, C2 minus C1 is just going to be just going to be an arbitrary constant. I'm not going to be able to get the y out of that nicely, so not out of the sign in a way that's going to combine nicely with a y squared, so I'm just going to leave it like that, and that's okay. I can leave my answer like that. I'm fine with that. Okay, so we're going to do one more example here, and I really like this example. Where this one is related to is, let's say you're talking about population growth. Okay, so I'm just going to kind of do an aside here before I get into this. So population growth, the rate at which a population grows, okay, let's say is the change in population over the change in time. I shouldn't say equal to. We know that the rate at which a population grows should be proportional to the size of the population. Okay, the speed that it grows should be related to how big the population is. The bigger the population is, the faster the population should be growing. Okay, so that's the relationship that we have here, and we know that what that means is, okay, that there should be a constant between the two of them, or as a factor in there, I should say. So the rate at which the population grows should be equal to some constant multiplied by the population. Now that constant is going to end up being built by, you know, the death rate, the birth rate, immigration, like there's a whole bunch that goes into it. It can be quite complicated, but as just a basic example here, that's a good idea of how the relationship works here. Now let's go back over here. So let's split this up here. Now notice that there is no x part of this. Well, what I can do here is move the y over and make that k dx. Now I integrate both sides, and this is going to end up becoming the natural log, okay, of the absolute value of y. Okay, and this is going to end up being kx plus some sort of arbitrary constant. Now, actually, I should have had the arbitrary constant over here, but I think you've seen me do this a couple of times. You know that there is an arbitrary constant here that I just move over and add to this one. Well, now to get y by itself, I'm gonna convert this in forms here. I'm going to make this y equals e to the kx plus c. Okay, because I'm just going to convert this to exponential form. Okay, and now that works here. Okay, I'm totally fine with that. I don't need the absolute values anymore. And now watch this. I can do a little bit more here because this is going to be e to the kx multiplied by e to the c. Okay, that addition in there implies multiplication between two powers here. And now e to the c is just going to be an arbitrary constant. So I can write that as c multiplied by e to the kx. It's really neat that in a question here that really could be used to model population growth, that we get this natural logarithm, the base of the natural logarithm popping out of that. It's just a really cool result here. Anyway, hopefully that gives you a bit of a sense of how the separation of variables procedure for solving simple differential equations works.